time those trucks have. In mining, time saved translates directly into profit.
They are built to move mountains, carve the earth, and reshape entire industries. But behind their steel frames and raw power lies a quieter truth. These machines do not forgive mistakes. A single swing, a missed signal, a moment of miscalculation, and lives can be lost in seconds. Across mines, tunnels, and construction sites, engineers pushed scale further and further, believing bigger meant safer, faster, and more efficient. Instead, danger grew with every added ton of steel. Some of these machines bankrupted companies, others erased landscapes. All of them changed how humans work at the edge of survival. This is the story of the deadliest heavy machinery ever built, and the risks we accepted to control the earth itself. Big Musky Dragline Excavator, the coal mining giant. Big Musky Dragline Excavator was one of the largest land-based machines ever constructed, and a symbol of how scale transformed coal mining in the United States. It was built in 1969 by the Bucyrus-Erie Company for Central Ohio Coal Company, a subsidiary of American Electric Power. The machine was assembled in southeastern Ohio, near the town of Cumberland, specifically to operate in strip mines extracting coal for electricity generation. Big Musky weighed approximately 13,500 tons and stood nearly 22 stories tall when fully assembled. Its most defining feature was a bucket capable of holding 100 cubic yards of material, large enough to lift more than 300 tons of earth in a single scoop. The dragline was powered entirely by electricity rather than diesel fuel, drawing power through a trailing cable connected to the grid. Each movement of the machine required massive energy input and precise coordination. The purpose of Big Musky was not to dig coal directly, but to remove overburden, the thick layers of soil and rock covering coal seams. Before machines of this scale, strip mining relied on smaller drag lines and a large workforce operating in sections. Big Musky changed that balance. A single machine could replace dozens of smaller units, reshaping entire landscapes in months rather than years. Operation began in 1970 and continued until 1991. During that period, Big Musky moved more than 600 million cubic yards of material. However, its size introduced new dangers. Mechanical failures occurred at heights where rescue was difficult or impossible. Workers faced constant risks from cable snapbacks, bucket swings, electrical hazards, and structural stress. Accidents did not always involve the machine collapsing, but even minor errors could be fatal due to the scale involved. Economically, Big Musky contributed to the decline of smaller coal operators. Only large utilities could afford the purchase, maintenance, and energy costs associated with such a machine. As coal prices fluctuated during the 1970s and 1980s, operating Big Musky became increasingly expensive. Environmental regulations also tightened, increasing the cost of land reclamation after strip mining operations ended. By 1991, Big Musky was no longer economically viable. It was shut down and left standing as a dormant structure until dismantling began in 1999. Most of the steel was sold for scrap, but its massive bucket was preserved and placed on public display as an industrial monument. The legacy of Big Musky remains controversial. Supporters viewed it as a technological achievement that maximized output and reduced labor costs. Critics argued it accelerated environmental damage and concentrated risk into single points of failure. In historical assessments of American coal mining, Big Musky is frequently cited as an example of how extreme mechanization solved short-term production problems while creating long-term economic and safety challenges that reshaped the industry. Bagger 288, Bucket Wheel Excavator, the Moving Mountain. Bagger 288, Bucket Wheel Excavator earned its reputation as the largest land vehicle ever built and one of the most intimidating machines in industrial history. It was constructed by the German company Krupp in 1978 for the Rheinbraun Mining Company, now part of RWE, to operate in the Hambach lignite mine in North Rhine-Westphalia, Germany. The machine stands approximately 96 meters tall and stretches over 220 meters in length. It weighs an estimated 13,500 tons and moves on 12 tracked bogies, each supporting enormous loads. Bagger 288 uses a massive rotating bucket wheel fitted with 18 buckets, allowing it to excavate thousands of tons of earth every hour while advancing continuously across the mine. Bagger 288 was designed to remove overburden, not coal itself. Its task was to strip away soil and rock above lignite seams so smaller machines could extract fuel for power plants. When it entered service in 1978, it replaced fleets of excavators and conveyor systems, dramatically increasing efficiency while reducing the number of workers directly involved in excavation. Despite its slow top speed of roughly half a kilometer per hour, Bagger 288 is extremely dangerous. Its size creates enormous blind zones where vehicles and workers can disappear from view. Any mechanical failure, structural crack, or control error can escalate quickly because stopping the machine is neither fast nor simple. Electrical systems alone require constant monitoring, as the excavator consumes as much power as a small town during operation. The environmental impact of Bagger 288 has been just as significant as its engineering legacy. Entire villages were relocated to allow the Hambach mine to expand, and vast areas of land were stripped and reshaped. While German law requires land reclamation, the scale of disruption created by a single machine remains controversial among environmental groups and mining communities. Bagger 288 continued operating through the 1980s, 1990s, and into the 21st century, supported by continuous upgrades and maintenance programs. It became internationally famous in 2009 when it appeared briefly in popular media, reinforcing its image as a mechanical giant. Operating Bagger 288 required a specialized crew trained in electrical engineering, structural monitoring, and long-range planning. Routine inspections were conducted daily, and major components were serviced according to schedules measured in years rather than hours. Transporting the machine between mining sections involved dismantling conveyor links and coordinating ground stabilization, as uneven terrain could threaten balance and structural integrity. Today, Bagger 288 stands as a symbol of industrial extremity. It represents how engineering ambition can push machines beyond human scale, concentrating power, risk, and environmental impact into a single moving structure. In mining history, Bagger 288 is remembered not just for its size, but for redefining how much destruction and productivity one machine can deliver. Caterpillar D11 Bulldozer, built for extreme terrain. The Caterpillar D11 bulldozer is one of the largest and most powerful bulldozers ever placed into commercial service, designed specifically for environments where conventional equipment cannot operate safely. It was introduced by Caterpillar Incorporated in 1986 as part of the company's effort to dominate large-scale mining, quarrying, and heavy earth-moving operations across the world. Production of early variants began in the late 1980s, with continuous updates introduced from the 1990s onward. The D11 was built to operate in open-pit mines, coal fields, and remote construction sites where ground conditions are unstable and loads are extreme. Depending on configuration, the machine weighs more than 100 tons and is powered by a diesel engine producing over 800 horsepower. Its elevated sprocket design separates the drivetrain from ground shocks, increasing durability while allowing the bulldozer to push massive volumes of rock, soil, and overburden for extended periods. What makes the Caterpillar D11 particularly dangerous is the environment it is designed to enter. The machine is often deployed on steep slopes, loose spoil piles, and unstable terrain where landslides and ground collapse are constant threats. Operators work from enclosed cabs positioned several meters above ground level, relying on visibility systems and spotters to avoid rollovers, collisions, and ground failures. A single misjudgment can result in the machine sliding uncontrollably or tipping, incidents that have caused fatalities in mining operations worldwide. The D11 plays a critical role in mine preparation and reclamation. It is used to clear access roads, push blasted material, and reshape land after extraction. During the 1990s and 2000s, demand for the D11 increased as mining companies consolidated operations and prioritized fewer, larger machines capable of working continuously. This shift reduced labor needs but increased risk concentration, as failures involved equipment far heavier and more difficult to recover than earlier bulldozers. Maintenance of the Caterpillar D11 is a constant concern. Components such as tracks, blades, and hydraulic systems experience extreme stress. Regular inspections are required, and shutdowns can last days or weeks when major repairs are needed. Fires caused by hydraulic leaks and engine overheating have also been documented, particularly in hot climates and high-load conditions. Despite these risks, the Caterpillar D11 remains in active service today, with newer models incorporating improved safety systems, digital monitoring, and reinforced operator protection. Its legacy is tied to the industrial push toward machines that can dominate terrain rather than adapt to it. In mining and heavy construction history, the D11 stands as an example of how power and productivity increase alongside danger, making survival dependent on precision, training, and constant vigilance. LeTourneau L2350. Wheel loader, the largest loader ever. The LeTourneau L2350 wheel loader holds the distinction of being the largest wheel loader ever built, representing the peak of scale in the surface mining support equipment. It was developed by LeTourneau Incorporated in the late 1990s and officially introduced in 1998, targeting large open pit mines that required constant loading of ultra-class haul trucks. Production continued after LeTourneau's mining division was acquired by Joy Global in 2011 and later by Komatsu in 2017. The L2350 was engineered for one purpose: loading massive mining trucks as efficiently as possible. Depending on configuration, the machine weighs more than 260 tons and is powered by a 16-cylinder diesel engine, producing approximately 2,300 horsepower. Its bucket capacity can exceed 40 cubic yards, allowing it to load trucks such as the largest haul trucks in only a few passes. This level of output dramatically reduced cycle times in large-scale operations. Despite being a loader rather than an excavator, the L2350 is considered extremely dangerous due to its size and operating environment. It functions in tight coordination with haul trucks, blasting zones, and active mining faces. Visibility around the machine is limited, and ground personnel are prohibited from approaching while it is operating. Any miscommunication between loader operator and truck driver can result in collisions, crushed vehicles, or fatal injuries. The L2350 is commonly deployed in copper, iron ore, and coal mines across North America, South America, Australia, and Africa. During the 2000s, as mining companies focused on maximizing output with fewer machines, loaders like the L2350 became central to production. This concentration of capacity increased economic efficiency, but also meant that mechanical failure could halt entire operations. Maintenance is a constant challenge. Tires alone can weigh more than 6 tons each, and replacement requires specialized lifting equipment and controlled procedures. Hydraulic systems operate under extreme pressure, and failures can release energy violently. Fires caused by fuel leaks or engine overheating have occurred in large loaders industry-wide, often spreading rapidly due to the volume of combustible materials on board. From an economic perspective, the L2350 contributed to the decline of smaller loading equipment. Only large mining companies could justify the purchase price, maintenance infrastructure, and skilled workforce required to operate it safely. This reinforced industry consolidation during the late 2000s and early 2010s. The LeTourneau L2350 remains in service today under updated branding, with incremental improvements to operator safety and monitoring systems. Its legacy is not defined by speed or mobility, but by sheer force. In mining history, the L2350 stands as an example of how productivity at extreme scale carries proportional risk, where a single mistake can have irreversible consequences. F60, overburden conveyor bridge, the longest land vehicle. The F60, overburden conveyor bridge is recognized as the longest land vehicle ever built, a machine designed to move earth on a scale unmatched by any other ground-based structure. It was developed in East Germany by Wirtgen during the late 1980s for use in large lignite strip mines. The first F60 unit entered service in 1991 at the Lichterfeld open pit mine, marking a new phase in continuous mining operations. The F60 measures approximately 502 meters in length, making it longer than many ocean vessels. It stands around 80 meters tall and weighs more than 13,000 tons. The machine moves on multiple rail-mounted bogies and operates as a mobile bridge, carrying conveyor belts that transport overburden from excavation sites directly to dumping areas. Instead of relying on fleets of trucks, the F60 enabled uninterrupted material transfer across vast mining zones. The primary role of the F60 was to remove overburden covering lignite seams. Bucket wheel excavators cut into the earth, and the material was fed onto the F60's conveyor system, which carried it across the pit to designated disposal zones. This integration allowed mines to operate continuously, reducing fuel use and minimizing the need for truck-based hauling. Despite its efficiency, the F60 introduced a significant danger. The machine's size created extreme structural stress, and its slow but constant movement left little margin for error. Workers operating on elevated platforms faced risks from falls, mechanical failures, and electrical hazards. The conveyor belts alone extended hundreds of meters, and any malfunction could propagate through the entire system. Emergency shutdowns were complex and time-consuming due to the scale of operations. In 1992, one F60 unit suffered a partial collapse caused by structural overload and foundation instability. Although no fatalities occurred, the incident highlighted the inherent risks of operating such a massive structure on unstable ground. Repairs took months and required extensive reinforcement, demonstrating how failure at this scale could halt production entirely. The economic impact of the F60 was mixed. Large, state-backed mining operations benefited from reduced transport costs and higher output. However, smaller operators could not afford the infrastructure required to support such a machine. This accelerated consolidation within the lignite mining sector during the 1990s, particularly in regions transitioning from state-controlled to market-based economies. As environmental concerns grew and lignite mining declined in parts of Europe, several F60 units were retired. One machine was preserved at Lichterfeld and converted into an industrial monument, allowing the public to walk along its structure and understand its scale firsthand. Today, the F60 stands as both an engineering milestone and a cautionary example. It demonstrates how industrial ambition can push machines beyond conventional limits, concentrating productivity, danger, and environmental impact into a single structure. In mining history, the F60 is remembered not only as the longest land vehicle ever built, but as a symbol of the risks inherent in extreme mechanization. Marion 6360. Walking dragline, the machine that walks. The Marion 6360. Walking dragline is one of the most extreme examples of surface mining machinery ever constructed, designed to operate at a scale where traditional mobility systems become impractical. It was built by the Marion Power Shovel Company in the late 1970s for large strip mining operations in the United States. The machine entered service during a period when coal demand was high, and mining companies pursued maximum efficiency through extreme mechanization. Unlike wheeled or tracked machines, the Marion 6360 moves by walking. This design was necessary because the machine's weight exceeds 12,000 tons, far too heavy for conventional transport systems. Instead of rolling, it uses massive cam-shaped shoes that lift and reposition the entire structure forward in slow, deliberate steps. Each movement shifts thousands of tons of steel and requires careful coordination to avoid ground failure. The dragline stands over 20 stories tall when fully assembled and is equipped with a boom extending more than 100 meters. Its bucket can hold dozens of cubic meters of material, allowing it to remove enormous quantities of overburden in a single pass. Like other draglines of its class, the Marion 6360 does not extract coal directly. Its role is to strip away soil and rock to expose coal seams for later processing. Operation of the Marion 6360 is inherently dangerous. The machine's slow movement creates a false sense of stability, but its immense mass places constant stress on the ground beneath it. Operators must account for soil composition, moisture levels, and previous excavation patterns. A miscalculation can cause uneven settling or structural strain, increasing the risk of mechanical failure or collapse. Workers servicing the machine face additional hazards. Maintenance often occurs at extreme heights, with limited access routes and exposure to electrical systems carrying vast amounts of power. Cable failures, bucket swing incidents, and structural fatigue have all been documented risks associated with walking draglines. Emergency evacuation is difficult due to the machine's size and isolation within active mining zones. The Marion 6360 operated primarily during the 1980s, a period when large-scale strip mining dominated coal production. However, as energy markets shifted and environmental regulations increased, machines of this scale became less economically viable. The cost of operation, maintenance, and land reclamation began to outweigh the productivity benefits offered by a single, massive dragline. By the early 1990s, many walking draglines, including the Marion 6360, were retired or dismantled. Advances in smaller, more flexible equipment reduced the need for machines that concentrated so much risk and capital into one structure. Portions of these draglines were scrapped, while select components were preserved for historical reference. The Marion 6360 remains a powerful symbol of industrial ambition. It represents a time when mining engineering prioritized dominance over terrain, even at the cost of safety and sustainability. In the history of heavy machinery, the Marion 6360 is remembered not just for its ability to walk, but for illustrating the limits of scale when human control is stretched to its absolute edge. Komatsu D575A superdozer, the world's biggest bulldozer. The Komatsu D575A superdozer is widely recognized as the largest bulldozer ever placed into production, a machine built to handle conditions where conventional earth-moving equipment could not survive. It was developed by Komatsu Limited of Japan and introduced in 1981, with full-scale production models entering service during the 1980s. The bulldozer was designed specifically for large surface mining operations, particularly coal mines requiring extreme pushing power. The D575A weighs more than 150 tons depending on configuration and is powered by a 12-cylinder diesel engine producing over 1,000 horsepower. Its blade, when fully equipped, can move more than 70 cubic meters of material in a single push. This capability allowed the machine to clear massive volumes of overburden quickly, reducing the need for multiple smaller bulldozers working in tandem. What set the Komatsu D575A apart was not speed, but brute force. It was engineered to operate in environments filled with loose spoil, fractured rock, and unstable ground created by blasting. These conditions are among the most dangerous in surface mining. Operators work near active excavation faces, steep drop-offs, and constantly shifting terrain where ground failure can occur without warning. The superdozer introduced significant safety challenges. Its sheer size created enormous blind spots, making ground personnel extremely vulnerable. Strict safety protocols were required, including exclusion zones and radio coordination, to prevent workers from approaching the machine during operation. Rollovers, blade strikes, and ground collapses were constant risks, particularly on steep slopes common in strip mines. The Komatsu D575A saw its most extensive use from the 1990s into the early 2000s, especially in large coal operations in North America and Australia. During this period, mining companies favored fewer, larger machines to maximize output and reduce labor costs. While economically efficient, this strategy concentrated risk. Mechanical failure or operator error involving a machine of this scale could result in catastrophic damage and loss of life. Maintenance of the D575A required specialized infrastructure, components such as tracks, hydraulic cylinders, and blade assemblies were so large that repairs often took days and required heavy lifting equipment. Fires caused by hydraulic leaks and engine stress were also a documented concern, particularly during prolonged high-load operation. Production of the Komatsu D575A eventually declined as mining practices evolved. Environmental regulations increased reclamation costs, and advances in alternative equipment reduced reliance on single-purpose mega-bulldozers. Komatsu later introduced updated models focused on efficiency and digital monitoring rather than pure size. Today, the Komatsu D575A stands as a landmark in heavy machinery history. It represents the peak of bulldozer scale, where engineering pushed power to its practical limit. In mining operations, it is remembered as a machine capable of reshaping entire landscapes, while reminding operators that extreme size brings equally extreme danger. Terex RH400 Hydraulic Excavator, the deadliest swing. The Terex RH400 hydraulic excavator is regarded as one of the largest hydraulic excavators ever built and one of the most dangerous machines routinely operating in open pit mines. It was originally developed by Orenstein and Koppel in Germany during the late 1990s and entered service in 1997. In 1998, Terex acquired the design, later passing the model to Bucyrus in 2010 and eventually to Caterpillar following its acquisition of Bucyrus in 2011. The ARH400 was engineered for large-scale surface mining, particularly copper, iron ore, and coal operations. The machine weighs approximately 980 tons and is powered by twin diesel engines producing a combined output of more than 4,000 horsepower. Its bucket capacity ranges from 45 to 100 cubic meters depending on configuration, allowing it to load ultra-class haul trucks in only a few passes. What makes the RH400 especially dangerous is the combination of reach, mass, and hydraulic force concentrated in its boom and bucket. A single swing of the upper structure moves hundreds of tons of steel and material. In active mining environments, this swing radius overlaps with haul roads, blasting zones, and support equipment. Any miscalculation in positioning or timing can result in collisions that leave no chance for survival. The excavator's operating environment further increases risk. RH400 units are positioned near unstable mine faces, where rockfalls and slope failures are common. Operators rely on geological monitoring and constant communication with ground crews, yet conditions can change rapidly after blasting or heavy rain. Structural stress on the boom and stick assemblies must be carefully managed to avoid fatigue failures. Visibility is another critical hazard. Although the operator sits high above ground level, blind zones around the machine are extensive. Smaller vehicles, maintenance crews, or survey teams can disappear entirely from view. Strict exclusion zones are enforced in modern operations, developed after multiple fatal incidents involving large hydraulic excavators industry-wide during the 2000s. Maintenance of the RH400 presents additional dangers. Hydraulic systems operate under extreme pressure, and failures can release energy violently. Component replacement often requires technicians to work at height, beneath suspended loads, or near energized systems. Fires caused by hydraulic oil leaks and engine heat have also been recorded as a serious risk in high production cycles. The Terex RH400 saw widespread adoption from the late 1990s through the early 2010s, becoming a benchmark for large hydraulic excavation. Its productivity reshaped mine planning, allowing fewer machines to move greater volumes of material. However, this efficiency also concentrated risk, making each machine a critical point of failure. Today, the RH400 remains in operation under Caterpillar branding, supported by advanced monitoring and safety systems. Its legacy is defined by controlled power. In mining history, the RH400 stands as a reminder that when a machine's swing alone can be deadly, survival depends entirely on discipline, distance, and constant vigilance. Liebherr T282B mining truck, the 360-ton crusher. The Liebherr T282B mining truck is one of the largest haul trucks ever built and a defining machine of ultra-class surface mining. It was developed by the German manufacturer Liebherr Group and introduced in 2004 as an evolution of the earlier T282A. The truck was designed to meet the demands of large open pit mines where efficiency depended on moving enormous volumes of material over short but hazardous distances. The T282B has a nominal payload capacity of approximately 360 tons. When fully loaded, its total operating weight exceeds 640 tons. The truck is powered by a high-output diesel engine producing more than 3,600 horsepower, driving an electric wheel motor system that delivers torque directly to the rear wheels. This diesel-electric configuration allows precise control under extreme load, but introduces complex electrical hazards during operation and maintenance. The primary role of the T282B is to transport ore and waste material from excavation points to crushers or dumping areas. It operates continuously alongside hydraulic excavators, such as the largest shovel and excavator models. In these environments, haul roads are narrow, dusty, and often carved into unstable terrain. Grades, sharp turns, and blind intersections are common, increasing the risk of runaway vehicles and collisions. The greatest danger associated with the T282B is its scale. The truck's blind spots extend several meters in every direction, making smaller vehicles and personnel effectively invisible from the cab. Numerous fatal accidents in surface mining worldwide have involved ultra-class haul trucks running over light vehicles or ground workers who were outside designated exclusion zones. Once in motion, the stopping distance of a fully loaded truck is extreme, leaving no opportunity to correct sudden hazards. Mechanical failure also poses severe risk. Brake system malfunctions can lead to runaway incidents on downhill grades, one of the most feared scenarios in open pit mining. Tire failures are another critical hazard. Each tire can weigh several tons and is inflated to high pressure. Tire explosions during maintenance have caused serious injuries and deaths, leading to strict safety protocols introduced during the 2000s. The Liebherr T282B was widely adopted from the mid-2000s into the early 2010s, particularly in copper, iron ore, and coal mines in Australia, South America, and Africa. Its efficiency supported the industry trend toward fewer machines with higher capacity. While this reduced operational costs, it also concentrated risk. A single accident involving a truck of this size can shut down entire sections of a mine. Maintenance of the T282B requires specialized facilities and highly trained technicians. Work is often performed beneath elevated truck bodies or near high-voltage electrical systems. Lockout procedures and remote diagnostics were expanded as direct responses to serious incidents involving ultra-class trucks during this period. The Liebherr T282B remains a symbol of modern mining extremity. It represents how productivity and danger rise together at massive scale. In the history of heavy machinery, the T282B is remembered not only for how much it could carry, but for how easily it could destroy anything in its path. Demag CC8800-1. Crawler crane, 1 failure, total collapse. The Demag CC8800-1. Crawler crane is one of the most powerful lattice boom cranes ever built, designed for lifts where failure is not an option. It was introduced by Demag Cranes in 1999 as a heavy lift solution for power plants, refineries, offshore modules, and large-scale infrastructure projects. With a maximum lifting capacity of approximately 1,600 tons, the CC8800-1 represented the upper limit of mobile lifting technology at the turn of the century. The crane operates on a crawler undercarriage, allowing it to move short distances while carrying loads. Its modular lattice boom system can be configured in multiple arrangements, including main boom, luffing jib, and superlift attachments. Counterweights totaling hundreds of tons are suspended behind the crane to maintain balance during lifts. Every component must be assembled precisely, as even small deviations can compromise stability. What makes the CC8800-1 exceptionally dangerous is the physics involved. During heavy lifts, enormous forces act through the boom, rigging, and ground beneath the crane. Loads are often raised tens of meters into the air, passing over active construction sites and workers below. If a component fails, whether a pin, cable, weld, or ground support, the collapse is sudden and catastrophic. Unlike smaller cranes, there is no margin for partial failure at this scale. Several high-profile crane accidents during the late 1990s and 2000s, involving various heavy-lift cranes, led to increased scrutiny of machines like the CC8800-1. Investigations frequently cited improper assembly, miscalculated load weights, wind conditions, or inadequate ground preparation as contributing factors. In crane operations, ground-bearing pressure is as critical as the crane itself. If soil compacts unevenly under load, the entire structure can tip. Operating the CC8800-1 requires a highly specialized crew. Engineers calculate lift plans weeks in advance, accounting for load weight, radius, boom length, wind speed, and ground conditions. Operators rely on precise communication with riggers and signal personnel. Any breakdown in coordination can result in uncontrolled movement of suspended loads. Maintenance and transport add further risk. The crane must be disassembled into dozens of components for relocation, each weighing many tons. Assembly errors during reconfiguration have historically been a major cause of crane accidents. Workers often operate beneath suspended counterweights and boom sections during setup, where mistakes can be fatal. The CC8800-1 saw extensive use from the early 2000s through the mid-2010s in Europe, Asia, and the Middle East. It played a critical role in constructing power stations, wind energy infrastructure, and petrochemical facilities. Its productivity enabled projects that would have been impossible with smaller cranes, but it also concentrated risk into single lifts. Today, the Demag CC8800-1 stands as a reminder of how unforgiving heavy lift operations can be. In crane engineering history, it symbolizes a simple truth. At extreme scale, one failure does not cause damage. It causes total collapse. Joy 12. CM12, continuous miner, death underground. The Joy 12. CM12. Continuous miner is a heavy underground mining machine designed to cut coal directly from the seam while operating in some of the most dangerous environments in industrial work. It was developed by Joy Mining Machinery during the 1980s as part of a broader shift toward mechanized underground coal extraction. The 12CM12 model became widely used in the United States, Australia, and other coal-producing regions during the 1990s and 2000s. The machine operates using a rotating steel cutting drum fitted with carbide-tipped bits. As the drum spins, it grinds directly into the coal face, breaking material loose and feeding it onto an onboard conveyor. The coal is then transferred to shuttle cars or conveyor belts for removal from the mine. The Joy 12 CM12 weighs tens of tons and is powered by high-voltage electrical systems delivered through trailing cables that follow the machine through narrow tunnels. What makes the 12 CM12 especially deadly is the environment it works in. Underground coal mines are confined, dark, and unstable. Roof collapses, methane gas buildup, coal dust explosions, and equipment entanglement are constant threats. The continuous miner operates at the coal face, the most dangerous area of the mine, where freshly exposed rock has not yet been fully supported by roof bolts. The rotating cutting drum is a major hazard. Workers operating nearby risk being struck, pulled in, or crushed if they enter the machine's danger zone. Despite strict safety rules, fatal accidents have occurred involving miners caught between the machine and the coal rib or pinned against tunnel walls. The confined space leaves little room to escape once the machine is in motion. Electrical hazards are another critical concern. The Joy 12 CM12 relies on high-voltage power, often exceeding 2,000 volts. Damaged cables, moisture, and poor grounding can lead to electrocution. In underground conditions where water is common and visibility is limited, these risks increase significantly. Lockout procedures were strengthened in the 1990s following multiple fatal incidents linked to energized equipment. Methane gas presents an additional deadly factor. Cutting into coal releases methane trapped within the seam. If ventilation systems fail or airflow is disrupted, gas can accumulate rapidly. Sparks from cutting bits or electrical components can trigger explosions. Several major underground mining disasters during the late 20th century involved continuous miners operating in poorly ventilated sections. The Joy 12 CM12 was widely adopted from the 1990s into the early 2010s as mines sought higher productivity with fewer workers. While the machine reduced manual labor, it also concentrated danger around a single piece of equipment. When accidents occurred, they were often severe, leaving little chance of survival. Maintenance of the machine adds further risk. Repairs are performed underground, often in tight spaces beneath heavy components. Hydraulic failures, falling roof material, and unexpected machine movement have all caused fatal injuries during servicing operations. Today, continuous miners like the Joy 12 CM12 remain in use, supported by improved sensors, remote controls, and monitoring systems. However, the fundamental dangers remain unchanged. In mining history, the Joy 12 CM12 represents how mechanization underground increases efficiency while placing human lives inches away from rotating steel, unstable rock, and explosive air. In these conditions, one mistake is often final. Wirtgen 4200 surface miner, the rock grinder. The Wirtgen 4200 surface miner is a heavy mining machine designed to cut solid rock directly from the ground without the use of drilling or blasting. It was developed by the German company Wirtgen Group and introduced in the early 2000s as part of a new generation of surface mining equipment aimed at improving precision and reducing explosive use. The 4200 model became one of the largest and most powerful surface miners ever produced. The machine operates using a massive rotating cutting drum mounted beneath its chassis. This drum is fitted with hundreds of carbide-tipped cutting tools that grind rock into a consistent material size as the machine advances. The Wirtgen 4200 can cut rock layers up to several hundred millimeters deep in a single pass, producing material that can be loaded directly onto conveyor belts or haul trucks. Fully assembled, the machine weighs more than 200 tons and stretches over 30 meters in length. The primary advantage of the Wirtgen 4200 is control. Unlike blasting, surface mining allows operators to selectively extract material with precise depth and grade. This made the machine popular in limestone, coal, phosphate, and iron ore operations across Europe, Asia, and the Middle East during the 2000s and 20s. It also reduced vibration damage near populated areas and industrial facilities. Despite these benefits, the Wirtgen 4200 is extremely dangerous. The cutting drum alone generates immense rotational force, capable of shattering hard rock continuously for hours. Any contact between the drum and personnel is instantly fatal. Strict exclusion zones are enforced, as flying debris and fractured rock can be ejected at high speed during operation. Dust is another major hazard. Grinding rock releases fine particulate matter that can severely impact respiratory health. In enclosed or poorly ventilated environments, prolonged exposure increases the risk of lung disease. Water spray systems are used to suppress dust, but failures or improper maintenance can quickly create unsafe conditions for nearby workers. The machine size also creates visibility challenges. Operators sit high above ground level, relying on cameras and ground signals to navigate. Smaller vehicles and workers can disappear entirely from view. Accidents involving surface miners and support equipment have occurred when communication protocols were not strictly followed. Maintenance operations present additional risks. Cutting tools must be replaced regularly due to extreme wear, requiring technicians to work beneath or near the drum. Lockout procedures are critical, as accidental rotation during servicing can be deadly. Hydraulic systems operate under high pressure, and failures can release energy violently. Economically, the Wirtgen 4200 contributed to changes in mine planning. Its ability to replace drilling, blasting, and crushing operations allowed companies to streamline production. However, this also reduced workforce size and concentrated operational dependence on a single machine. When breakdowns occurred, entire production lines could be halted. Today, the Wirtgen 4200 remains in service with updated monitoring and safety systems. Its legacy lies in redefining surface mining through mechanical cutting rather than explosives. In heavy machinery history, it stands as a reminder that grinding solid rock on an industrial scale demands absolute control. When that control is lost, the consequences are immediate and irreversible. Herrenknecht tunnel boring machine trapped below ground. Herrenknecht tunnel boring machines are among the largest and most complex underground machines ever built, designed to excavate tunnels through soil and solid rock where human access is extremely limited. The company Herrenknecht AG was founded in Germany in 1975 by Martin Herrenknecht and became the global leader in tunnel boring technology during the 1980s and 1990s. Its machines have been used in subway systems, railway tunnels, road tunnels, and water transfer projects across Europe, Asia, and the Middle East. A tunnel boring machine, commonly called a TBM, operates as a moving underground factory. The cutting head at the front can measure more than 15 meters in diameter and is fitted with dozens of rotating cutters designed to grind through rock. Behind the cutting head are multiple sections containing motors, hydraulic systems, conveyors, ventilation equipment, and crew compartments. Large TBMs can weigh more than 3,000 tons and extend over 100 meters in length. The danger of a Herrenknecht TBM lies primarily in its environment. Work takes place deep underground, often hundreds of meters below the surface, where escape options are limited or non-existent. Workers operate inside the machine while it advances slowly through unstable ground. Ground pressure, water ingress, and unexpected geological changes can turn routine operations into emergencies within minutes. One of the most serious risks is tunnel collapse. If ground pressure is miscalculated or support systems fail, surrounding earth can shift suddenly. Several tunnel accidents worldwide from the 1990s to the 2010s involved TBMs becoming trapped or buried due to ground failure. In these situations, workers may be sealed inside sections of the machine for hours or days while the rescue operations are organized. Flooding is another major threat. TBMs often operate below water tables, relying on pressurized systems to keep groundwater out. Seal failures or sudden breakthroughs into water-bearing layers can flood tunnel sections rapidly. In confined underground spaces, rising water leaves little time for evacuation and can cut off power, lighting, and ventilation. Mechanical hazards are constant. The cutting head rotates with enormous force, and internal conveyors move broken rock continuously through the machine. Maintenance tasks require strict lockout procedures, as accidental activation can be fatal. Electrical systems operate at high voltage in damp conditions, increasing the risk of electrocution. Heat and air quality also contribute to danger. Deep tunnels can reach extreme temperatures, and ventilation systems must remove dust, exhaust, and gases. Failure of ventilation has caused serious incidents where workers suffered from heat stress or oxygen depletion. Herrenknecht TBMs became essential to modern infrastructure from the 2000s onward, enabling tunnels that would have been impossible using conventional drilling. However, their scale concentrates risk. When something goes wrong underground, help is far away and options are limited. In heavy machinery history, Herrenknecht tunnel boring machines represent engineering mastery combined with extreme vulnerability. They operate where collapse, flooding, and mechanical failure offer no easy escape. Underground, survival depends entirely on planning, monitoring, and the assumption that rescue may not come quickly. Bucyrus-Erie 2570-WS dragline, the final giant. The Bucyrus-Erie 2570-WS dragline is often considered the final evolution of the ultra-large walking dragline, built at a time when mining companies pushed machinery to its absolute physical and economic limits. It was manufactured by Bucyrus-Erie in the late 1980s for large-scale strip mining operations in the United States, primarily to remove massive volumes of overburden covering coal seams in the Midwest and Appalachian regions. The 2570WS was an enormous machine, weighing more than 13,000 tons when fully assembled. It stood over 20 stories tall and featured a boom extending more than 100 meters in length. Its bucket capacity exceeded 100 cubic yards, allowing it to lift hundreds of tons of rock and soil in a single pass. Like other draglines of its class, it did not move on wheels or tracks. Instead, it used a walking mechanism that lifted and shifted the entire structure forward using large camshoes, a slow process that placed extreme stress on both the machine and the ground beneath it. The purpose of the Bucyrus-Erie 2570WS was efficiency through scale. By removing overburden faster than any smaller machine, it allowed mining companies to expose coal seams rapidly and reduce reliance on multiple pieces of equipment. During the late 1980s and early 1990s, this approach aligned with industry goals of maximizing output while minimizing labor. However, the size that made the 2570WS productive also made it dangerous. The machine operated at great height, with maintenance crews working far above ground near high-voltage electrical systems and massive moving components. Cable failures, structural fatigue, and bucket swing incidents posed constant risks. Emergency response was difficult due to the machine's isolation within active strip mines and the time required to descend safely from elevated work areas. Ground stability was another major concern. Walking draglines exert enormous pressure on soil, and uneven settling could lead to misalignment or structural strain. Operators had to account for moisture levels, soil composition, and previous excavation patterns before every move. A miscalculation could damage the walking mechanism or compromise the integrity of the entire structure. By the mid-1990s, economic conditions began to shift. Coal prices fluctuated, environmental regulations tightened, and land reclamation costs increased. Machines like the 2570WS required vast amounts of electricity, constant maintenance, and specialized crews. As mining companies reassessed costs, the extreme scale of such draglines became a liability rather than an advantage. Many ultra-large draglines were retired during the late 1990s and early 2000s, including the Bucyrus-Erie 2570WS. Some were dismantled for scrap, while others were partially preserved as industrial landmarks. No larger walking dragline would be built afterward, marking the end of an era in surface mining design. In mining history, the Bucyrus-Erie 2570WS represents the final chapter of gigantism in dragline engineering. It stands as a symbol of how far industry was willing to go in pursuit of productivity, and how the risks, costs, and consequences of extreme machinery ultimately set practical limits on size.